To determine the full load amps for 700 horsepower motor operating on a 3-phase 480 volts alternating current power supply, we need to use the power equation for a 3-phase system. Firstly, let's convert horsepower to kilowatts. 700 horsepower is equivalent to 522.1 kilowatts. This conversion is essential because electrical calculations typically use kilowatts. Secondly, the power equation for a 3-phase motor is power equals voltage times current times power factor times the square root of 3. In this equation, power is measured in kilowatts, voltage in volts, current in amps, and the power factor is a dimensionless value representing the efficiency of the motor. A typical power factor for a motor is around 0.85. However, it's important to refer to the motor's nameplate for the exact power factor value, as it can vary slightly depending on the motor's design and operating conditions. In our calculation, we'll use 0.85 as the power factor. Substituting the known values into the equation, we have 522.1 kilowatts equals 480 volts times current times 0.85 times the square root of 3. The square root of 3 is approximately 1.732. Now let's rearrange the equation to solve for current. Current equals power divided by voltage times power factor times the square root of 3. Plugging in the values, we get current equals 522.1 kilowatts divided by 480 volts times 0.85 times 1.732. Simplifying the denominator, 480 volts times 0.85 times 1.732 equals approximately 707.7. Now, we have current equals 522.1 kilowatts divided by 707.7. Remember that 522.1 kilowatts is equal to 522,100 watts. So, current equals 522,100 watts divided by 707.7. Performing the division, we find that current equals approximately 737.7 amps. Therefore, the full load amps for 700 horsepower motor operating on a 3-phase 480 volts alternating current power supply is approximately 737.7 amps, based on the assumption of a power factor of 0.85. It's crucial to remember that this calculation provides an estimate. Always refer to the motor's nameplate for the exact full load amp rating. The nameplate value is the most accurate and reliable source for determining the motor's current draw. Furthermore, when selecting conductors and overload protection for the motor circuit, it's essential to comply with the National Electrical Code or NEC and any other applicable local codes. The NEC provides guidelines for sizing conductors and overcurrent protection devices based on the motor's full load amps. For example, NEC section 430.22 addresses the minimum size of conductors supplying motors. It typically requires conductors to have an ampacity of not less than 125% of the motor's full load current. This ensures that the conductors can safely handle the motor's current draw without overheating. Similarly, NEC section 430.52 provides guidelines for sizing motor branch circuit short circuit and ground fault protection. The type of protection device, such as a circuit breaker or fuses, and its maximum allowable rating depend on the motor's full load amps and the motor's design characteristics. Proper overcurrent protection is essential to protect the motor and the electrical system from damage due to short circuits or ground faults. In addition to conductor sizing and overcurrent protection, it's also important to consider the motor's starting current. Motors typically draw a much higher current during starting than during normal operation. This inrush current can be several times the motor's full load amps. Therefore, it's essential to select motor starters and other control equipment that are capable of handling the motor's starting current. Different types of motor starters, such as across-the-line starters, reduced voltage starters, and variable frequency drives or VFD, are available to manage the motor's starting current and provide smooth acceleration. Reduced voltage starters, for example, limit the motor's starting current by applying a reduced voltage to the motor during startup. VFD provide even more control over the motor's speed and torque, and they can also reduce the motor's energy consumption. When installing a motor, it's also important to ensure proper grounding. Grounding provides a path for fault current to flow back to the source, which helps to trap over current protection devices and prevent electrical shock hazards. The grounding conductor should be sized according to the NEC and should be properly connected to the motor frame and the electrical system grounding electrode. Regular maintenance is also essential for ensuring the motor's reliable operation. This includes inspecting the motor for signs of wear and tear, lubricating bearings, and cleaning the motor to prevent overheating. Overheating can significantly reduce the motor's lifespan and can even cause motor failure. By following proper installation and maintenance practices, you can ensure that the motor operates safely and reliably for many years. Finally, remember to always consult with a qualified electrician or electrical engineer for any electrical work. Electrical work can be dangerous, and it's essential to have the proper training and experience to perform it safely. A qualified professional can help you select the right equipment, install it properly, and ensure that the electrical system meets all applicable codes and standards. To summarize, calculating the full load amps for a 700 horsepower motor involves using the power equation for a three-phase system, considering the motor's power factor, and referring to the motor's nameplate for the exact full load amp rating. It also involves complying with the NEC and other applicable codes for conductor sizing, overcurrent protection, and grounding. Proper installation, maintenance, and consultation with a qualified professional are all essential for ensuring the motor's safe and reliable operation. The process involves converting horsepower to kilowatts, applying the power equation relating power, voltage, current, and power factor, and then solving for the current. Remember to consult the motor's nameplate for the most accurate full load amp value and power factor, and always adhere to the NEC guidelines for safe installation and operation. Therefore, the calculated full load amps is an approximation based on a typical power factor. Real-world applications might see a variance in current depending on the load and the actual power factor of the motor. It is also crucial to remember to account for any potential voltage drop in the system. If the voltage at the motor terminals is lower than the rated 480 volts, the motor will draw more current to deliver the same amount of power. Therefore, it is important to measure the voltage at the motor terminals under full load conditions and adjust the calculations accordingly. In conclusion, understanding the principles of motor amperage calculation combined with adherence to safety standards and professional expertise ensures a safe and efficient electrical system design and operation. Always prioritize safety and consult with qualified professionals for any electrical work.